All right. So yes, I know I got cut off. I didn't lose track of time. Anyway, I got going. So what we have again here is the magnetic field or the magnetic pole orientation inside of the Earth. So south magnetic is close to north geographic, and vice versa. And if we look at the magnetic field lines of the Earth, they extend out beyond, lost one. They don't cross. They never cross. This one's got to go out farther. They go out beyond the surface of the Earth. This side is drawn way better. The arrows point in at the top and out at the bottom, because we come out from the north and in at the south. And so the direction of the arrow here over North America is pointed at north geographic. Whether you're here or you're here in your rotation, the arrow on your compass points at north geographic, which is where the South Pole is attracting the north end of the little magnet. This magnetic field is essential to life on Earth because the sun is a very turbulent mass of moving charges and moving particles, and it frequently has vast explosions that toss charged material, protons and high-speed electrons, out into space toward the Earth. And the magnetic field of the Earth is a giant windshield for us. In other words, as the charges approach from the sun, they get deflected around the Earth by the magnetic field, and then they train off behind. The little bits of the solar wind that funnel in at the north and the south poles spiral in along the magnetic field lines, and they're accelerated by the magnetic field lines, and then they interact with our atmosphere and light it up just like a fluorescent light bulb, and create the aurora borealis. There is the aurora borealis is the northern lights. The aurora australis is the southern lights, and they are mirror images of each other. So when we can see the northern lights, we also have the southern lights in very much the same pattern. Okay, so enough astronomy for the moment. Now, I want to talk about magnetic forces. The magnetic force is equal to QVB sine theta, where Q is the charge that you are pushing around with the magnetic field. V is, so charge is in coulombs. V is the velocity in meters per second. B is the magnetic field. Strength in Tesla. And theta is the angle from the B vector to the V vector. Okay. So we get our strongest forces when the sine of theta is equal to 1. So when theta equals 90 degrees. So if my my magnetic field and my velocity are at 90-degree angle, that's going to give me the largest possible force. If they're less than a 90-degree angle, then I get less than the maximum force. And so the direction of force we get by the right-hand rule. Okay, so the right-hand rule is based on your right hand. So let me draw a typical diagram for determining the right-hand rule. So if I have a magnetic field that is pointed in this direction, and we often in diagrams show magnetic field with multiple lines, just because we get lots of magnetic field lines in our diagrams, we're going to draw multiple magnetic field lines on a small diagram. And I'm going to draw my velocity with a single arrow. For denoting directions into and out of the board, I'm going to use kind of the arrow mentality. If you think about, Robin Hood and his merry men, and you have fletched arrows, right? If I look at this end, I'm going to see the point of the arrow as it spreads out, right? So this is pointing out of the surface. You're looking at the point of the arrow. Over here, we see either a plus or a cross, depending on whether the feathers are this way or this way. Those two symbols are used for pointing in. Okay? And that becomes important because when we talk about these right-hand rule, we're looking for 3 different directions. Okay? We use our right hand, our fingers equal the direction of B. Our thumb equals the direction of velocity, like if you'd hitch a ride. And the palm points in the direction of force on a positive charge. Okay, so for this diagram, I'm going to start with my right hand. I'm going to put it on so that my fingers are lined up, pointing at the ceiling, which is which direction these arrows are pointed. I'm going to rotate my hand until my thumb points in the direction of velocity, and then my force is aligned with the palm of my hand. So if I was going to push with my hand, it would push forward out of the board. And so I would denote the direction of my force as arrow pointing forward. Okay? If I had another example where I had my magnetic field shown by crosses and my velocity pointing at the ceiling, see if you can figure out which way the force would be. Okay? Start out with your fingertips pointing in to the board, right? You're looking at the back end of my elbow, right? That's the direction of my B field. I turn my hand until my thumb aligns with the velocity, and then the palm of my hand pushes in the direction on a positive charge. So my force on a positive charge would be that direction. Force on a positive would be that direction. The force on a negative would be simply the opposite, because negatives do the opposite of what positives do. Okay, so what I encourage you to do is to stick to the right hand rule. Use your palm to predict the force on a plus, and whatever that direction is, the opposite direction for force on a minus. Okay, we got a little bit of time for a few more examples. Okay. Fingers, with right hand, point in the direction that the arrows are pointing. Rotate your thumb around. The strongest force would occur if my thumb was perpendicular, but it's not. It's stretched out even farther, so I can't push as hard. Okay, so my force pushes outward, and the direction for outward is the point of an arrow, right? Because my right hand force would be pushing this way. And I'd have to take the sine of the angle in here to figure out what fraction of the maximum force I would get when I multiplied by sine of theta. Okay, let's try one more. Let's say that we have a force in this direction on a charge that is moving in that direction, and I want you to figure out the orientation of the magnetic field. Okay, so I want my palm to show force. I want my thumb to orient. Nope. Yeah, there we go. My thumb to orient toward V. Right, my palm pushes up this way. My thumb is pointed in the way that I'm hitchhiking. My fingers are pointing directly into the board. So that means I'm going to see the X's. I'm kind of disappointed that you guys are going to take this test on your own, because it's very entertaining to sit up at the front of the room and watch everybody doing gymnastics. Anyway, okay, I'm going to leave it off there. I'm going to put a little bit of an assignment up that'll have some calculation with force equals QVB sine theta, and some that are right hand rule orientation things, and maybe a couple of magnetic field maps if they're available. On Thursday, we'll focus on applications. So how to make a speaker, how to make a solenoid, how to make a motor, things like that. And we'll go from there. So thanks much. See you on Thursday.